Today we cover contextual retrieval. Doesn't RAG already retrieve context? Isn't that already a thing?
That's the whole thing it does. Yeah, absolutely.
Yeah. So what is it that we're doing additionally here? Is it kind of like the advanced or hybrid retrieval techniques that we've covered in the past?
Think of contextual retrieval as doing retrieval with more context. So we're retrieving our chunks contextually, as in where those chunks exist in the context of their source document.
So we're getting the context of the context. We're almost playing a meta context game here, huh?
That's right. That's absolutely right.
That's reminiscent of leveraging metadata. I see a lot of patterns here. Maybe we can bring it all together before the end. What do you think?
I think we could bring it all together before the end.
I think we can too. All right. We got quite a bit to string together. I look forward to seeing the demo today. Should be a banger. We'll see you back in a bit. Welcome, everybody. Today, we are covering contextual retrieval. I'm Dr. Greg, and I am here with the LLM Wizard, aka The Wiz. We are here to talk about the latest sort of breakthrough or kind of next level RAG approach. This is directly from Anthropic, came out late September, mid-September, and we saw it and we thought, wow, that's just a perfect way to sort of bring together a lot of the content that you might be familiar with us covering already, and then just kind of take it to the next level a little bit. And we really liked this. We wanted to showcase it. And if you can understand contextual retrieval, which is made up fundamentally of contextual embeddings and a contextual best matching 25 approach, you're in a really good place with your understanding of state-of-the-art RAG systems. So if you have questions along the way, please throw them into the Slido link, or also probably we can handle some YouTube live chat questions today. So let's go ahead and get into it. Is this really next level RAG, or is it kind of the same thing we've been talking about all along? Let's find out. As we align our aim to the day, we want to kind of target a couple of things. Number one, we want to really break down this contextual retrieval. We're starting to get really down in the weeds with having to pull apart the words here when we get to something like this. So we're going to do our best to do just that. It's made up, as the authors tell us, of contextual embeddings and a contextual BM25 or best matching 25 approach. It's not exactly traditional RAG. It's not exactly hybrid retrieval. It's kind of both and then some. We're going to discuss the pros and cons of using an approach like this, computational efficiency versus performance, of course. And we're going to actually build a contextual retrieval application, do some benchmarking on it, see if this, in fact, does improve scores with a tool that we're familiar with, tool like RAG assessment. All right, so let's kind of get into this. Now, we're going to kind of approach this piece by piece. Contextual retrieval is what exactly? I'm going to walk you through it. Wiz is going to walk you through the code. As we get into the concepts, let's just set a little context. First, a quick primer on prototyping. And this is going to allow us to zoom in on the way this kind of came about from Anthropic. Okay. Then we're going to dig into some of the technical details. When we talk about prototyping LLM applications, we're often using four primary prototyping patterns: prompt engineering, RAG, fine-tuning, and agents. When we talk about prompt engineering, we're just talking about putting stuff in context. We're typically using the in-context learning design pattern to build LLM applications today. Fine-tuning, of course, is just teaching the LLM how to act, how to behave. We're really trying to just dial in input-output behavior. RAG, which is the focus of today, is about giving the LLM access to new knowledge. And really what we're doing with contextual retrieval is dialing in exactly the right knowledge, the right amount, the right type of knowledge. Agents are typically going to come in to enhance the search and retrieval process. And you'll notice today that contextual retrieval is also just trying to enhance the search and retrieval process. So really, this is where a lot of effort is going today with a lot of the developments that we're seeing coming out. So we're typically starting with prompt engineering. We're going to try to optimize what we're putting in context. That's going to bring us to RAG. We'll also downstream often want to optimize the way our input and output schemes work within our embedding models and our chat models. Typically, we're going to use both of these things. We might also use some agentic reasoning behavior within any of these specific patterns, but there's one way in particular that we're probably going to use the agentic enhancement of search and retrieval. As we get started, we're going to prompt. And really, this is where a lot of the work is going to get done. As we go one shot, two shot, few shot, we're going to do some evaluation. We're going to see how that's going. We haven't left prompting yet. And this is the kind of place that Anthropic came out with something in September, and they said, you might not need to leave prompt engineering, but if you do, maybe check out contextual retrieval. After this is when we're typically looking at adding some new knowledge with RAG. Then we're going to look at the chunks. Okay, we're going to say, how can we kind of optimize the way that we're getting the context and putting it in context? That chunk size optimization is typically something we think of as just how big is the chunk, but we can go further, as we'll see today. Then we might do something like fine-tune embeddings before we start to apply some of these advanced retrieval techniques. This is where we might enhance the retrieval with some agentic behavior before finally we might do something like fine-tuning a model. Now let's zoom in on what we're going to talk about today. We're going to talk about these pieces. We're going to talk about how RAG and optimization of the chunks and the advanced retrieval process and enhancing it with search specifically is kind of all contained within this contextual retrieval approach. So, fine point. Why are we talking about this now? Well, in August, prompt caching came out from Anthropic. And this is something that if you follow our channel, you're quite familiar with the idea of prompt caching. If you've got a specific query or input that the user is going to leverage a lot, you can simply cache the output. So you don't have to actually run inference each time that you're getting another same old question. This typically works very well up to a certain point, because up to a certain point, you kind of really don't want to dump all of your data directly into the prompt every time. But you can up to about, let's say, 200,000 tokens. This is what Anthropic is suggesting. There's about 500 pages of material. So just sort of dumping the whole knowledge base in. This is something that is quite straightforward and a great way to get started prototyping. As you try to sort of dial in how to move beyond this, that's where we start to get into this more interesting space. So you kind of don't need to leave prompt engineering until you get to a certain level of corpora, the data you're plugging in. If it's lots and lots and lots, if you're dealing with a really large knowledge base, you're going to have to do something a little bit more sophisticated, something a little bit more scalable. This, of course, is where RAG comes in. And RAG isn't just looking through everything in the prompt straight up. We're putting everything in context. We're being more selective about finding our reference material, about adding the specific reference material. And then in the end, that's going to give us slightly better answers, particularly when we can't just dump our whole entire data set in context. And so scalable RAG is about giving the LM access to new knowledge that is somewhere within our large knowledge base of information. We ask a question, we typically send it to an embedding model. That embedding model is looking for semantically similar stuff that's in our corpus, in our data. And the stuff that we find is then returned to a prompt that's already been set up with a nice template. Basically says, use the context, don't lie to me. The stuff that's returned is kind of basic, naively matched. It's returned in no particular order. There are ways we can make it more sophisticated, and indeed we should. This retrieval process is very basic. It's very naive in general, but we can get more and more sophisticated with what we put in context when we're doing RAG. All of this retrieval is happening before we actually do our generation with the chat model and get our better answer. So kind of in 3 easy steps, you can kind of think about the important piece of this is really creating the vector store, taking the data, putting it into a searchable database where we're splitting up the docs into chunks. That is, docs in a natural language processing sense, could be a whole ton of PDFs, but the sort of doc is the chunk, really. The document is kind of representative in general of any part of our corpus. And then we're creating embeddings for each of these chunks. We're storing those embeddings in the vector store. And, it's important to remember the only thing in there is chunks. So that's what we're retrieving. Now, let's sort of take a moment to realize, in general, if we ask any given question for any given chunking strategy, there is going to be a, quote, correct or right or best chunk for that question. This is sort of something that we can say in general. And so you might say, like, when we ask a question, we want to go into the document. If we're doing this as a human, we're going to find sort of the answer somewhere. This is kind of the idea of what we might call a golden chunk, right? So golden chunk is the chunk that best represents the context needed to answer a specific question. And one question you might ask is, well, don't I need more than one chunk sometimes, though? Like, don't I actually need multiple chunks? So, Wiz, let's just chat about this for a second. If I sort of have a golden chunk, do I just always need one perfect golden chunk, or sometimes I actually need, this piece that's sort of described in the chunk is connected to this other piece of the story. I kind of want all of it at once. So some questions actually need more than one chunk, don't they?
Yeah, absolutely true. The idea is that there's this, multi-hop questions or questions that do require more than one piece of context, right? This is a classic way to test to make sure that your retrieval system is working very well, etc. So is one chunk enough? Probably not for all questions, but it's trivial to imagine situations where we can construct one chunk being enough. For instance, having LLMs ask questions about specific chunks, right? That's going to be a way to very straightforwardly make sure that there's an answer for each chunk.
That's right. That's right. Okay, so then if some questions require more than one chunk, what's the utility of this idea of like a golden chunk? I mean, you sort of want there, in this sort of ideal world to be one perfect chunk that's going to give you the right answer. What's the utility in general? And then, kind of maybe if you can foreshadow a bit, what's the utility today?
Yeah, the idea is that we know that this chunk contains some answer to some questions based on the document that we provide, and being able to tie responses to that exactly is extremely useful in helping us locate the correct chunk or chunks, right? Also casting this wide net and then potentially narrowing it down thanks to things like well, just to foreshadow a little bit, or perhaps give it away, re-ranking, is going to be a huge benefit as well.
Yeah, like I'm just kind of struck, not to belabor the point, but this came out of Anthropic said, yo, we just did prompt caching. It's pretty dope. Basically, the whole corpus of text is one chunk. So in that case, like that's the golden chunk. It's the whole thing, right? And so now as we move into a more sort of scalable, I have tons and tons. There's no way I'm gonna shove it all in to the context window. There exists some chunk, right? So some knowable amount of text that if we could just get all of that stuff into one chunk, man, that would just be the best, right?
It would be pretty good.
Yeah. Well, let's see if we can with this amazing new contextual retrieval. Let's keep going. We'll see you back. So in general, we don't just have one chunk, right? We have all the relevant chunks because one chunk might refer to the other chunk. And, we're saying chunk a lot here. And there's a lot that we need to make sure that we're digesting here, all of the chunks. The retrieval process itself, we can kind of separate the idea of chunking from the idea of retrieval, but they are inherently, intrinsically connected. And the retriever that we use is important. The chunk size that we use is important because they all go into the idea of doing retrieval correctly. If we do retrieval really well, we do generation really well. Okay. All that's fine. Okay, so then what exactly is the problem? Well, the problem is that what we're doing in RAG is we're using embedding models. And when we use a specific kind of embedding model, like the embedding models that we typically use for RAG, is we're embedding representations of our data so that we can quickly retrieve them. And we're doing this based on similarity. We're doing this so we can search the data for stuff that's similar. That means semantically similar. That means it means roughly the same thing. The way we implement this is through a naive retrieval process, kind of at the very baseline. You can get obviously more sophisticated with this, but down in the weeds, we're doing some sort of similarity calculation, typically a cosine similarity, where we're kind of just looking, is this thing close to this other thing in embedding space? But interestingly, when we go to semantic similarity, we lose some of what we had when we did classic search, when we did classic retrieval. Specifically, we lose some of the exact match capability that we might have had before in more classical approaches, sort of the Googling technique, let's say, where exact matches are kind of what we get back. So we want to kind of take the semantic similarity approach and the exact match keyword approach and we want to kind of combine them into a better solution. And we can do that with tools that we already know about. For instance, the BM25 or Best Matching 25 ranking function ranks documents, this is important, based on query terms that appear in the context chunks. So here we're looking for the precise word or phrase that matches. This is obviously exactly kind of where we want to be. Now, going back even a little bit further into classic NLP, we can say in general that there are kind of two types of embedding models. We can kind of look at ones that are looking at the position of words relative to other words, or we can look at ones that kind of just jumble them all together, kind of the classic bag of words approach. The ones that really don't look at how things are related and in sequence to one another, those are the ones we're kind of zooming in on, because the relatedness and sequence to one another is kind of giving us that semantic similarity. But we already have the semantic similarity with our other approach. So we can leverage this kind of no context approach, funny enough, to get better context. If we define, again, context as the position of words relative to one another. We're focused here, again, remember, on exact match keywords. So BM25, what it does is it builds on these classics, the term frequency, inverse document frequency concept, which measures how important a word is to a document in a collection. So BM25 is sort of a refined version of this that considers the document length and then has this like cool like saturation function. And it helps to prevent very common words from dominating results. Okay. Example, directly from Anthropic. This is a great example. Imagine the query. You're a technician, you're looking for the answer in your service manual. The query is error code TS999. Well, this is going to kind of be well handled from like an error code perspective by the embedding model and the similarity matching approach. I'm going to look for stuff that's like error codes. But if I take the BM25, aka sort of, TF-IDF approach, that's not really leveraging how words are kind of, right next to each other or not. It's kind of looking at what is the specific keyword. It's going to do a better job helping me figure out what's going on with that TS999. That's important too. I want both of these things, not just one of them. And anytime I want both of these things, I'm going to do, of course, an ensemble approach, just like we've always done in machine learning. So what's the ensemble here? Well, it's exactly the same kind of thing we've been talking about in all of the hybrid retrieval strategy stuff, advanced retrieval strategy stuff that you may be familiar with already. This reciprocal rank fusion approach, if we want to be fancy, is just sort of able to take two different pieces. Again, keyword search. Look at that. We got our similarity matching through dense vector retrieval, and it's able to create an even better result. This better RAG is something we all sort of know about already. And the process might go something like this. We break down the knowledge base, the corpus, into chunks, right? All these little chunks. Usually the chunks are a few hundred tokens each. Then we're going to create TF-IDF encodings, and we're going to create semantic embeddings. We're going to create not just a vector database, but we're also going to create an index for our TF-IDF encodings. Then we can use both the vector DB and this index from our query to get both results, which can be combined using a reciprocal rank fusion. And if we dedupe results, we can actually get sort of a better top K for the context chunks we put into the prompt as reference material. Okay, perfect. So great. Now we can scale then. Perfect. But then what's the problem? Or I guess what's the next problem? Well, consider this question. What was the revenue growth for whatever corporation in this quarter? And you might say, well, revenue growth 3%. Boom. Nailed it. However, if we look at this a little bit closer, we're actually putting this into the prompt. We're actually putting the company and previous quarter into the prompt. We could obviously be a lot more specific than the company and previous quarter. In fact, we probably should if we had the golden chunk, right? And so what we want to do is we want to leverage this idea of getting chunk specific explanatory context. And what we'll do is, as Anthropic calls it, we'll prepend this chunk specific explanatory context. So rather than say the company, the previous quarter, what are we going to say? Well, we could say this chunk is from an SEC filing on Acme Corp's performance. Okay, it's pretty sick. A little metadata kind of built in there to the chunk. The previous quarter's revenue was 314 million. Ah, beautiful. So I get the percentage and I get enough information to tell me about what it was and what it probably is now. So this is a lot more powerful, especially when you start to get into, well, what if I want a prediction of future quarter? What if I want to assume some baseline growth that is part and parcel? What if I want the final revenue for a few quarters out from now? As we know, the LLMs are pretty good at this kind of thing now. They're obviously much better if you give it the right input information. So this idea of contextual retrieval is that if we can prepend this information to the chunk, okay, if you've been falling asleep and you're kind of like, yeah, I know all this. This is the important part. All of this happens before we embed this thing, before we do what we need to do with RAG. So we're getting all of the good stuff into the chunk first. We're getting the golden chunk first. Just like when we started chunking the docs in the first place, before we embed them. Okay, this is key, because if you can put all of this into the chunk, right, you can imagine if you have this huge corpus, well, now all of a sudden you have this really explanatory, contextual information in each chunk, all of the stuff that's related to SEC filings Q2 2023 is going to be in a similar place in embedding space, versus if that chunk didn't have that explanatory context, I'm not going to kind of be able to locate that in the same place in embedding space relative to all the other stuff from the same document. Again, think large corpus. Don't think single PDF. Think many, many, many documents. Think about scaling this, right? Okay, so how do we get that? Well, it's actually really simple, and it's not hugely computationally demanding to do this. There's a simple prompt, and it goes something like this. Here's the doc. Here's the chunk. Please give a short, succinct context to situate this chunk within the overall document for the purposes of improving search retrieval of the chunk. Improving search retrieval. Beautiful. Answer only with the succinct context and nothing else. So this allows us to sort of add this new layer in here. This new layer of chunk, 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 run the prompt for each chunk, situate it in the document. So then we have context plus chunk, context plus chunk, context plus chunk. Again, the chunk is context. So again, the sort of the disambiguation of the language of this word context here is quite important. And that happens before, always before we go and we create our vector DB or we create our TF-IDF index, BM25, whatever it may be. Because recall, and as always will be true, if we do search and retrieval better, we can do generation better too. And of course, if this is just an advanced retrieval process in the end, downstream, we can get a little boosty boost with re-rank. We should probably do that too. And so in the end, this sort of combined retrieval that is now more than dense vector retrieval. It's an ensemble retrieval process that leverages sort of pre-embedding context addition. We can combine that now with a re-rank approach. So we perform the initial retrieval. We'll pass the top chunks along with the query through the re-ranking model, and then we'll use the re-ranking model. It turns out they did some really cool analysis here. They did a ton of different permutations, and it turns out they were like, well, how many chunks is the right size in the end to get? What should the top K number be? Is 5 chunks enough after I go through this crazy process? Is 10 chunks enough? Turns out 20 chunks was pretty sick. And so we wanted to find out, is that true? Did that work? Can we make it work quantitatively with something like RAG assessment? So when we went back to a classic here, Alice in Wonderland, and we're going to kind of take this approach that we just outlined. We're also going to add a little re-ranking. And since they called out in the paper, they didn't really have time to add this re-ranker, we thought, well, good opportunity for seeing, does it do any better? Let's find out. And head over to the Wiz to show us and walk us through contextual retrieval for RAG with re-ranking and Ragus. Let's get after it.
Yes, okay. Thank you, Greg. So, we are doing, I'm going to zoom in so you can see my screen a little bit better. We're doing a lot in this notebook, so, keep that in mind. Okay. First things first, the data set we're going to use today is this Alice in Wonderland. Just the whole thing, everything. It's lots of text, as you can see, big old text. Okay, cool. Second thing we're doing in the notebook is we are going to, to kick off the notebook, we need a ton of dependencies. So there are just approximately 100 or so dependencies here. All good. It is what it is. What we're going to do is we are going to look at this from a perspective of naive RAG first. So naive RAG is kind of our grounding that we're going to use. And we're calling it naive RAG. It is still using, as you'll see, the ensemble retrieval process. But we are going to start with this just simple kind of solution. Okay, so when it comes to our data, we're going to load it in using the text loader. Who knew? We're going to, make sure that we split it into chunks. We're choosing an arbitrary chunk size here. As far as I can tell, there is no specific reason to there is no specific reason to use a unique chunk size here. The research didn't seem to indicate that, so all good. We're also looking at, I think probably most importantly, looking for this idea of our so there's a lot of different stuff going on. Okay, so we need to make sure that we get a test set for RAG assessment, RAGAS. We also need to make sure that we get this idea of, the correct way to evaluate chunks, which is going to be done through GPT 4.0, as you'll see. But to actually generate the synthetic data set, we're just going to use GPT 4.0 mini. We're going to generate a test size of 30, which is relatively small, to be fair, but that's okay. And then we're going to look at producing this CSV. The CSV is just this data set as an output. And then we're going to create Ensemble retriever from documents. So in all cases, in order to be quote unquote fair, right, in all cases, we want to use the same retriever. The only thing we want to actually have be different in this particular notebook is this idea of our the chunks themselves are going to have changes done to them. So as Greg mentioned, we're going to inject context into the chunks. That's like the big idea. You'll see here that we're just going to stick to a number of docs retrieved as 5 as a base. This is arbitrary. You'll see later that we're going to use the re-ranking pipeline, which will make things a little bit clearer. And then we're going to kind of go through this creating the Ensemble retriever. So the way that the Ensemble retriever works is pretty straightforward. Basically, there is the sparse and then dense vector search methods. We are going to combine both the sparse and dense vector search methods, and that's going to be all that we do. I'm going to very kind of quickly go through this actual prompt template here. We've seen it a million times. It's just the RAG prompt template. And then we're going to set up a few different LLMs. One LLM is going to be Anthropic's Claude 3 Haiku. We're going to use Claude 3 Haiku because that was what was used in the contextual retrieval explorations originally. There's no specific reason other than because they did that we need to use Claude. You're also going to see that we have this kind of very standard RAG chain where we do care about context. This is because we need to populate the retrieved context field in RAGAS in order to get metrics about, it's going to blow your mind, but the retrieved context. You'll also see that when we call it, we get, pretty good answers, right? So who is the rabbit? The rabbit is a character analysis in Wonderland by Lewis Carroll, specifically known as the white rabbit. He is depicted as hurried and anxious creature, often wearing blah, 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 blah. And then, of course, we have during the trial, the king insists that it cannot proceed until all the jurymen are back in their proper places. So this is like legit, but it's kind of, I don't know, it feels a little empty. It's quite long, which is nice, but otherwise feels a little empty. And then we're going to evaluate it. So we're going to use, our favorite RAG evaluation library, which is called RAGAS. You can see here, all we're doing is we're just looping through our data set and we're creating a new data set, which includes the required fields. So there are these 4 required fields: user input, response, reference, and retrieved contexts. You will see that this retrieved context is just a list of strings. You'll also see that we have this, response and contexts that we're pulling out of our chain. This is because we have the chain set up to give us both responses and contexts. Then we're going to convert that to a RAGAS evaluation data set. And then we're going to essentially just have this, act as our evaluation LLM. So that's going to be GPT 4.0. GPT 4.0 is pretty straightforwardly just going to be used to evaluate, right? That's it. And then we do the metrics, and then we get this the score. We're not going to worry too much about the score right now. And then we're going to look at our contextual prompt. So our contextual prompt is this idea that we have this document which has some kind of flow to it, right? Like the document exists in its entirety, as well as it exists separately in individual chunks in our corpus. So what we want to do is we want it, given the whole document, and remember, our document is all of this, right? So given the whole document and the chunk that we care about, what is the what is the context that would add to this chunk that situates it in the overall document for the purpose of improving search retrieval of the chunk, right? So this is a very specific thing we're doing. We're saying, given this the entirety of Alice in Wonderland, all 5 novels or whatever it is, we're gonna go ahead and I'm very sorry, given all 12 12 stories of Alice in Wonderland, give us where this chunk should live in that story, right? Now, this is not the only way to do contextual retrieval. We could have just as easily taken metadata, right, from Alice in Wonderland and injected it into the chunk. And this is all done with this idea that we're going to both convert this to a dense embedding. We're going to convert it to dense embeddings, as well as we are going to convert it to our sparse vectors. And what that's going to mean is that we're going to inject information that we can use to search. So all we do is we literally just loop through all of the documents, right? This is slow, very, very slow. It's in fact prohibitively slow, except Anthropic, as Greg mentioned when he was going through the concepts, right? There's this idea of prompt caching, where we're gonna be able to cache components of our prompt, and the component of our prompt we're gonna cache specifically, right, is this entire document. So we don't have to keep reworking this entire document into our memory. We're just going to keep it there. We're going to keep it in the prompt cache, and that's going to speed up the generation a lot. So the cell does still take a while to run, but it doesn't take 30 to 80 hours to run, which is what you might expect otherwise. You'll also notice when we look at our documents, right? So this is our very first document in our corpus. We get started the project Gutenberg, blah, 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 blah. And then we see this. We see this, right? This chunk is the beginning of the book, Alice's Adventures in Wonderland by Lewis Carroll, containing the table of contents in the first chapter, Down the Rabbit Hole. This chunk is the beginning of the book. Alice, it just doesn't repeat. That's fine. But the idea is that now, if we were to ask the question, right, what happens at the beginning of the Down the Rabbit Hole chapter, right, we're more likely to get this chunk than we are to not get this chunk. And that's kind of the whole idea, right? So what we want to see happen is we want to see this be true, and so that's what we do. All right, so we'll very quickly just look at the scores from our original run, which are 0.61 context recall, 0.30 factual correctness, and 0.56 faithfulness. Okay, so the scores are not super duper, right? But they're also, they could be much worse. When we do the same process with our contextual retrieval pipeline, something else we're going to notice is the responses are a little bit better, right? Like, what occurs during the trial? During the trial, various characters, including the king, queen, and jurors, are involved in a chaotic and nonsensical legal proceeding. This is something that we get because of that additional context, right? Because now we know from each of these chunks, we know where the trial is, right? We have a better idea of this idea of what trial is. And then when we finally evaluate, you'll see that we take a very small hit on context recall, but we get a pretty significant bump in both factual correctness and faithfulness from our from our response, which is huge, right? And this is because we've added that context as additional information for our vector embedding search. So that's basically what's happening in contextual retrieval. That's it. I mean, you would think it would be more than this, but it's really just this process of adding information about what context this chunk appears in the parent document that helps us search for better chunks, that makes sure the chunks that we're getting are more relevant, et cetera, et cetera. And so with that, I'm going to pass you guys back to Greg. But before I do, I'm going to remind you to like the video, subscribe, ring the bell notification. We're live every Wednesday talking about cool stuff. Okay, with that, I'll really send you back to Greg.
All right. Okay. So it seems like we've got a lot going on here then. But in the end, is it really that complicated? Let's see if we can wrap this up. Well, of course, Anthropic is like, hey, each of your choices matter here. Chunk boundaries matter, embedding model matters, the specific prompt you use for that custom contextualizer matters, how many chunks you have matter, running evals matters. And, they did look at, I encourage you guys to go check out the blog because there's some really cool papers that they discussed in the blog that are from, one of them's even from 22 years ago. Shout out to Miamisburg, Ohio and LexisNexis, doing like really similar stuff. They looked at semantic chunkers. They looked at all the state-of-the-art chunkers. They looked at a lot of best practices to date, and they sort of combined all of them into this one approach. So that's why we wanted to cover it. And let's see if this can kind of make sense to you guys, that RAG is the dense vector retrieval plus in context learning. If we want to do a slightly better RAG, we're going to do that dense vector retrieval plus that sparse retrieval using the BM25, the TF-IDF kind of keyword search level stuff, putting all that stuff in context. When we go and we do the contextual retrieval pre-processing, we take the chunks, we run them through the custom contextualizer prompts, effectively getting data about the data, right? A little metadata action. The better chunks are then added to this better RAG approach. So we're sort of stacking. And in the end, what we have is this thing that they've called contextual retrieval, which is simply contextual embeddings plus contextual BM25. And that is all done, again, prior to the generation. So please do throw your questions into the Slido and let us know what questions you have. Wiz, I've got some questions to kick us off here. I just want to start with the metadata piece because it's so important to sort of think about how you might do similar stuff, but with a slightly different approach as we've done elsewhere. Like we didn't use agents or reasoning here necessarily as we might with metadata and as with approaches we've used in the past. But if we ask like, hey, tell me more about the chunk you just retrieved using the rest of the data, we're actually asking for more data about the data, right? Like we're actually fundamentally getting metadata here, aren't we?
It's literally metadata. Yeah, I mean, and in fact, you can construct situations which are simpler, which are literally using something like metadata filtering, right? So, like, let's say, for instance, we wanted to be able to answer questions about exactly which Alice in Wonderland story they were referring to. We might have a metadata filter where we classify which story the question is about or which stories the question is about, and then pass those stories in to metadata as filters, right? But the difference is with this approach is it allows us to do that across all of the chunks in our corpus, all of the documents in our corpus, as well as making sure that we if they ask questions that fall outside of these reasonable bounds or outside of our plan, they're still getting that additionally enriched retrieval. So it's like if metadata filtering is a very focused, very engineered approach, this is lets us kind of generalize and have a little bit more of fuzzy boundaries when we're doing our retrieval.
Okay. And I've got one more question, just because we only covered one type of data here before we dig into the audience questions. So we covered like fiction data, which, presumably is a little bit less challenging than some other types of data that you might see, code data or stuff in like a textbook. When might you want to really leverage an approach like this? Is there a specific type of data in your mind, beyond fiction, that really is like, man, that would potentially be really useful here? I mean, to me, it's like if you were looking for how part of the code base connects to another part of the code base, that sort of jumps out to me. Is that right? And what jumps out to you?
Yeah, there's all kinds of, I mean, any kind of data that can be enriched by contextual information, placing it within the overall corpus, right? Which is like the non-answer. That
Yeah.
that includes things like code, right? Where does this function exist? What context does this function exist in the code, right?
That's right.
Not to mention that for traditional retrieval, code's a bit of a sticky wicket, because obviously when I'm searching for code, I'm probably searching in English, and code is famously written in code, not English. But we
That's
have this
right.
idea of, it's, I know it's such a belabored example, but it's also the one that I like the best.
Yeah.
Imagine you have a textbook, and the textbook has Bernoulli's equation in it, right? If you just have a chunk that has Bernoulli's equation, and then I ask the LLM, what is Bernoulli's equation,
Hmm.
right? It's not going to get Bernoulli's equation. The retriever doesn't have an understanding. It's not, the equation isn't called that.
You'd have to
You know what I
type it
mean?
in, like,
Yeah,
specifically. Yeah.
it's got like, it's an equation.
Yeah.
This kind of adding of context to that helps for, think of it this way. In my belief, this approach works best when we are asking questions in natural language of things that are not traditionally represented by natural language.
They are encoded, let's say.
Oh, they're encoded.
Oh, okay. So, first question is, can you talk about the difference? And then I'll go ahead and sort of relieve the slides here. If you have questions, please throw them into the Slido. Can you talk about the difference between sparse vector search and keyword search, and how we were using the sparse search language here today?
Yeah, so think of it this way. If I search my document for, what is a cat or something like that, right? I know it's trivial, but like, this is the way to think about it.
That's right.
If I have documents that refer to, these cat-like creatures and this and that and this and that, I might get great results. But like, really, what would be even easier is just looking for chunks that have the word cat in it, right? Like, that's the idea, the difference between sparse vector search and keyword search. Keyword search is just looking for the word, literally, right? It's just saying, is this word in chunk? If yes, it's good chunk. If no, it's bad chunk. Sparse vector search is kind of doing that, but it's doing it in a slightly more convoluted way, where we're using this vector representation. We're normalizing it so that we can use cosine similarity, and then we're still thinking about like the meanings of these things as they relate to the corpus that they're in. So that's that TF-IDF approach versus just like, give me chunks that have the word cat in them.
Yeah. So the TF-IDF is like, we were using the sparse vector search as different from the dense vector search that we were
That's
using
right.
with the embeddings, and it's not quite keyword search. Like, it's a little bit more complex. It's a little bit more encoded than that. It's a little bit more,
Yeah.
And so we have this sort of dense vector retrieval. That's sort of the embedding model, and then we've got the sparse vector search. That's sort of the TF-IDF BM25 stuff. Is that right? And we're kind of getting a keyword search like result with that. So we don't have to explicitly do keyword search in addition. Is that right?
Yeah. So yeah, the question is asking between the difference between sparse vector search and keyword search. We are drawing the difference between dense embedding representations, so dense vector search and sparse vector search, when we're talking about our embedding representations in our vector store and then our BM25 search. BM25 search is much closer to a keyword search
That's
than
right. Okay,
embedding.
there we go. All
Yeah,
right. We got there. Okay,
but
so then,
it is a sparse vector search method.
okay, so I want to
Yeah.
go. I want to go to the bottom question here on the Slido here. So because it sort of double clicks in on this, it was clear for semantic search, but does this method actually improve on that BM25 search if you just use BM25?
Yes. Yes.
Okay, speaking
Period.
of improvement, it didn't really give that great improvement score-wise. What should we take from this?
I think in actuality, it's just it is a great improvement. I mean, like, this is so when we're talking about what is and is not or we're trying to understand the magnitude of change, right? With something like Ragus, we have to remember that Ragus is only useful for directional signal, as in, did this change make better or make worse? Made better. Trying to map out how much better is comes down to the quality of the data, the generated data set, which in this case was relatively low. Comes down to the way that we've chosen some of these metrics, right? So, like, if we wanted to, we could now do some bigger hyperparameter search, figure out exactly the right values, and start optimizing. But it is a great improvement score wise because it improved the score. That is the only thing that we care about. From there, now we can think about getting from, let's say this is 60% of the efficacy. We're going to get to, or effectiveness, or we're going to get to 80% by tweaking and changing. The idea though is just by adding contextual information and nothing else, the score on our test set went up, right? Which is extremely low hanging fruit.
Numbies go up.
Yeah, exactly. Numbies go up. Yeah.
Yeah, and so I want to rapid fire a couple here. Do I have to use Anthropic? No, you can use any model, right? And then how much does chunk overlap matter for the quality? You mentioned it was sort of chunk independent as far as you could tell.
Chunk overlap.
Chunk size independent, I should say.
Yeah, so chunk overlap is always going to be kind of useful. It gets less useful when we're retrieving a larger volume of context.
Scaling. Yeah.
So when we're retrieving like 25 from each retriever, and then we're re-ranking down to say 10 or 20, it's going to be less effective chunk overlap than if we weren't doing that. Chunk overlap is useful in less in smaller systems because we increase the chance that we hit the right context and that our context isn't straddled between chunks. But because we have this whole document and we're adding that contextual information based on this chunk's existence in the whole document, we mitigate immensely the idea that we might accidentally chop off some important piece of context.
Got it. Okay, so last question, and I just want to address this because it's a great entry point into digging deeper. Jan asks, would the results be even better when combined with semantic chunking? There was sort of a specific line in the paper that had a lot of reference material, and it, quote, "It is worth noting that other approaches to use context to improve retrieval have been proposed. They include adding generic document summaries to chunks. They experimented with those. Hypothetical document embeddings, summary-based indexing. They evaluated and saw lower performance there. So they looked quite closely at semantic chunking and even more advanced than semantic chunking strategies. I highly encourage you to check that out. We'll drop the link to the entry point to that question. I will personally drop the link right in the YouTube comments as soon as we're done here. But that is a wrap for today, everybody. Thank you for joining us for Contextual Retrieval. Is it next level RAG, Wiz? It's kind of next level RAG. I mean, in my opinion, right?
One of these things that as we get better at, as we get better at long context, as we get better at et cetera, these kinds of things will become table stakes. Yeah, absolutely.
Table stakes. You heard it here first. Advanced retrieval. If you're not doing advanced retrieval, you're still doing naive retrieval. Probably time to button that up and make sure that you're ready to rock and roll out at the edge with us. Wiz, thanks. I look forward to the next one. See you back next week. Thank you, everybody, for joining us for Contextual Retrieval Next Level RAG. We hope you learned something today, and we hope that we gave you some fuel to go build, ship, and share something awesome with a community. Speaking of, if you're not in our Discord community, please do join us. We'd love to have you in there. There's a whole bunch of legends, and they're always building, shipping, and sharing something awesome. If you're looking for more than the content we put out on YouTube or on GitHub, you might be interested in joining one of our upcoming cohorts. We've got one on LLM engineering. This is what's happening inside the LLM. How can you train, tune, align, and really dig into the guts of the transformer? That one's going from November to December. Cohort 3 should be a banger. And that's great material to sort of baseline and foundation yourself within the transformer. Attention is all you need paradigm before in January we kick off the AI Engineering Bootcamp Cohort 5, where we get much more into all the details behind something like contextual retrieval, agents, and much, much more from prototyping to production. That's a final wrap for today, everybody. We'd love to get your feedback, and always let us know if you'd like to see some specific type of content in the future. Until next time, keep building, shipping, and sharing, and we'll do the same. We'll see you all next week. Bye, everybody. Have a great rest of your Wednesday. See you soon.